So I first encountered this problem while I was solving the book Irodov, i.e. Irodov, I think. Right, so this problem basically says that A is a particle which is moving with constant speed and its velocity is always directed towards another particle B, and that particle is moving with constant speed as well, but along a horizontal line. So B is unaware of A, but A is trying to chase B. And that's why I written chase as the title of this graph. All right. So here's the setup. We'll define the angle theta as the angle between the vector BA and the x-axis. Then you will notice that integration of v cosine theta, or maybe I should say v cosine of pi minus theta, so that would be negative v cosine theta. So integration of negative v cosine theta dt, that is just the x component of the displacement of A. And using that, this complete problem can be dealt with very easily. But that's not sufficient for me. So instead, we will derive what this curve should look like and how is time related to all of this, and we'll do everything, right? So in detail, and we'll also learn how to solve such kind of questions where you have chasing happening. That is basically your velocity is dependent on the position, or I should say the relative position of the particles, right? So since we want relative position, maybe we should view everything with the eyes of B, because B is in fact just moving with U along the positive x-axis, and that means you can just subtract U from the velocity of A, the vector difference of course, and you will get the relative velocity. So that looks straightforward, I think. So according to B, this guy A, it's moving with velocity v vector minus u vector. Now we can decompose v vector along the x and y axis. Yes, that is one thing that we can do, but it would be even better if we decompose u along the radial unit vector and the tangential unit vector, because then you can use polar coordinates to describe everything, and you can basically find out what d theta upon dt, that is omega, what that will be, and what dr upon dt will be. So dr upon dt, that will just be the rate of increase of r. So over here u is supporting the increase of r and v is not supporting, and that's why u cosine of pi minus theta minus v. And of course, cosine of pi minus theta is just negative u cosine theta. So in the end, your r is decreasing, right? And so we get the first equation from this. So the first differential equation. And similarly, you can get something for d theta upon dt. So d theta upon dt is just the v tangential upon the radius. And in that case, in this case, it's just u sine of pi minus theta upon r, which is u sine theta upon r, right? So we have these two equations. Now, these two are not directly solvable because there's some problems, right? The first equation has theta in it, even though it's dr upon dt, and yeah, it's not solvable directly. Similarly, second equation has r in there, and it's just not good. So we want to eliminate either theta or r from one of these equations. So how do we do that? First of all, we'll divide these two equations. So dr upon dt upon d theta upon dt, that will just be dr upon d theta. Now look, that basically eliminated the time dependence of these equations, right? So now this becomes less of a question about the velocities and displacements and what the function in time is, and more of the question of how the curve actually looks. And we can write dr upon d theta equal to negative r times u cosine theta plus v upon u sine theta, right? It's dividing it. And then we'll define v upon u to be n, because, you know, notation. It's just something that I will do because I want to do it. Fine. And then we can solve these differential equations. I know it's very complicated to actually solve this, right? So you have to do all of this, and eventually you arrive at what r should be in terms of theta. But we are not done. What we actually need to do is we need to substitute this value of r in this equation. So the d theta upon dt equation will substitute r into that, and from that we can finally get the value of theta uh, given the time. So it's not as a function, unfortunately. So the value that you finally get is something like this. So it's not a function. I have not resolved this into a function yet, and I don't think I can. But this relation does give theta when you know what time it is. So that means, yes, we can figure out what theta is given the time. And now our main question is, uh, when will our radius, that is r, become 0? Because when that happens, your a and b, they finally meet, right? So when r approaches 0, so why did I use approach? Because as you can see, if you try to do this directly, you will run into not defined quantities, and it doesn't work like that. So instead, you need to see when r approaches 0, what exactly happens. So solve the whole equation. It's basically an equation, right? So you just get cot of theta upon 2 approaches 0, right? Because cosec theta plus cot theta, you can write that as cot of theta upon 2, and then that about n that approaches 0, because of course cosec theta, it cannot approach 0, right? It's bigger than 1 in this case. They are equal to 1, of course. And what that means is now we can just put cot theta equal to 0 in this equation for time, and we are done. We just get the value of capital D, which is the time required for A to catch up with B. And yeah, and another important thing is that as cot theta upon 2 should be 0 when r is 0, theta should be pi, because this basically means that cosine of theta upon 2 is 0. So theta upon 2 is pi upon 2, as theta basically goes from 0 to pi during this whole process. So it can only be pi upon 2, nothing else will work. And that means, yes, over here, as you can see, as B gets to the final point where they meet, A starts to go to the right as well. So it also starts going in the positive x-axis direction. Cool. And of course, you might be wondering, how did I get this curve? So I got this curve by doing this thing. So I think it's short and can be done easily, but not on a test, of course. But yes, you can do it and you will get this curve. It's not nice looking, it's very ugly. Even though there's this nice symmetry that you have between plus and minus over here, yes, that is okay, that's good looking, but overall it's not so nice. So we will not focus on what this curve actually looks like all that much, and we'll only focus on what the final capital T is, because that is the most important thing right now. All right, and that basically answers our question. And here I have made a bit of a graph that will show how it actually behaves. Right, so here I have used capital R instead of small r, and Z instead of theta. All right, and capital T and small t are still the same thing, right? And instead of using V, I'm just using U times N, because then I don't have to define that V over here. And as Z changes, so as our theta changes basically, you can see how this behaves. So you can see that over here, your vector, so the velocity vector for A, it's getting more and more horizontal until eventually it will basically approach the x-axis, right? And then it will become completely horizontal. Nice. So at pi, these should become the same, right? Even though it is not exactly looking the same, because of course this was a limiting case over here, but yes, actually it should become the same. So when it's slightly less than pi, right? So something like this happens, and yeah, look good, I think. From a far away perspective, this graph makes much more sense. From close up, you see that it's not actually representing what physically is happening, because it's a computer in the end. So it might run into some problems over there. But yes, this is nice and it works, right? Okay. And as you change n, your graph changes. So the geometry changes, right? But as you change U and L, the shape doesn't. I mean, when you change L, of course, the size changes. So it shrinks or gets really big or something like that. But when you change the speeds, right? If it's the same proportion, nothing happens to the graph, right? And this was, in fact, what I first discovered that. So the first thoughts of this question in my head were that this thing, this complete graph's geometry is independent of the velocities. It's only dependent on the ratio, right? And that is obvious from here. All right. So I'll see you guys in the next video.